type of in this video, what we'll be discussing is the translational motion or the rotational motion. So we are less concerned with the other types of motion that we have, and particularly we'll be discussing the moment of inertia of a rigid body, and that is given as I equals to mr squared. Now, if two objects are being rolled of the same masses are being rolled, okay, if two objects of different masses, let's say a nylon and a ball and a tiny ball, are being rolled, which of these ball will go further? The one that will go further is the one with the highest moment of inertia, so take note of that. And if we are asked to calculate the moment of inertia of several bodies with the same mass, what we do is we keep on adding their moment of inertia and extracting out the common mass which the three bodies have in common. So, and you can see that as an example in so we have our mass. They gave us our mass of three different particles and their respective radius or their distance. So using the formula of moment of inertia, you can as well calculate out your answer and write it out. So we have another example here. We have that two particles of mass m1 and mass m2, they are connected to a rigid body of a length a. So we have our length to be a, and we should show that the moment of inertia of the system about the axis to the plane passing through the center of the mass is mu a squared, where we are given the value of mu to be m1 plus m2. So they gave us the value of mu. Now, if we are to consider the moment of inertia, what we do is we have the different bodies, mass 1 and mass 2, and if r1 is representing the length of mass 1, it simply means that r2 will be the subtraction of length 1 from r1, that is a from r1, that is our r2. And of course, we are to consider the moment of the body. We have to consider the clockwise moment, which is equals to the anti-clockwise moment, and we already know that. So from this point, we made r1 the subject of the formula, and we have it to be that. But don't forget, what the question says is that we should make mu the subject. We should show that where is it? We should show that the moment of inertia of the system about an axis is perpendicular to the plane and is passing through the center of the mass mu a squared. That's what they asked us to show. Now, from equation 2, we can make a minus r1 the subject of the formula, and we have m1 r1 over m2. And when we substitute r1 back to a minus r1, we have a minus r1 to become m1a over m1 plus m2. So that's what we did. So substituting r1 and a minus r1, recalling that r1 and a minus r1 are the respective distance of the two masses. So we substitute them back to equation 1, which is m1 r squared plus m2 r squared. So m1 r1 squared plus m2 r2 squared, but r2 squared is now representing a minus r1 all squared, so we substitute that. Then what we'll do next is to factorize out the necessary things. We have m1 m2 over m1 plus m2 as factorized outside. So when we factorize this outside, we are left with m2a squared over m1 plus m2 plus m1a squared over m1 plus m2. Then we go again with another factorization. So after factorizing out m1 m2 over m1 plus m2a squared, you can see we are left with m1 plus m2 over m1 plus m2, and that gives us what? 1. So, but going back to the question, they gave us that mu equals to m1 m2 over m1 plus m2. So when we substitute it, we have it to be mu a squared. So we've already proved that. So we are asked to find the moment of inertia of a solid circular cylinder. Now, since a solid circular cylinder of a radius of height h, what we usually do to look for the moment of inertia of this case is we take the integral of the distance, the integral of the square distance with respect to the mass. That's, we're integrating with respect to the mass. So on recalling that mass equals to density times volume, we have that mass equals to density times volume, and when we integrate that, the volume of a cylinder is given as pi r squared h, and when we take the derivative of both sides, we have Vm, that's mass with respect to the radius, to the distance I mean. So we substitute dm back to the initial equation, we have it to be pi r raised to power 4 h dr, and when we integrate, we have that. Now the m equals to density pi r squared h dr. When we integrate both sides from this path, it simply means that we've taken m as the subject of the formula in this case. So when we integrate that, we have the density pi r raised to power 3h over 3. So don't forget, we can extract m, because we know that I is equals to m r squared, but in this case r is representing a squared, so we extracted out the mass from the moment of inertia, so we have I to be equals to 3 over 5 ma squared. So that is that for the introduction. This is just like an introductory class to dynamics of rigid motion. Thank you.